Hmm. There we go. Hey, Pamela.
Hi. That was a weird moment.
I know I unhid you, and you didn't unhide.
No, and I couldn't unmute myself. It was like it didn't want me to be here.
No, no. This is going to be a special show, a solo show for me.
I feel so loved by Google.
Yeah, where I ask myself questions and answer them. That's a great question, Fraser. I'm glad you asked. Well, hey, everybody. If you have no idea what this is, you have stumbled into a live episode of Astronomy Cast, which is our long-running, much-beloved weekly facts-based journey through the cosmos. We are going to be doing episode 373, the Becquerel experiment. Mais oui.
And we recently got an email from someone complaining that we actually take weeks off and being kind of grumpy at us. And so I just want to say we try to be weekly, but sometimes things happen like we actually go on vacations and have families or get sick.
Yeah.
So please.
You are the director of CosmoQuest and a professor at Southern Illinois University, Edwardsville. I am the publisher of Universe Today and the product manager for HeroX, a spin-off of the X Prize Foundation. A lot of work to be done, a lot of responsibilities.
And we do this as a passion project. We don't get paid to do this. We pay the folks, Preston, who does our editing, and Susie, who does our show notes and things like that. We do this because we love you,
Yeah.
and please love us back and don't send us hate mail.
Yeah, well, whatever, we can take it. Yeah, I don't know. Neither of us have taken a penny, I don't think. I haven't taken any salary from Astronomy Cast since we
No,
started.
we've
No.
paid for some travel and tech. We both
Yeah,
have
yeah,
gotten tech along the years, but
yeah. Not recently, though.
I can fix that. You
Oh,
just have
okay.
to come to the United States.
Like that's going to happen. Anyway, right. So we'll take some time. We'll do the show. You can ask some questions if you wish. Not only questions about the topic as we have proposed it, but also just anything you like. We'd love to talk about it. We'd love to get into an argument about manned spaceflight versus robotic space exploration.
Why? Why do we need to argue? No hate today. No hate.
There's no hate. We argue with love.
Okay.
But I'm going to say hi to Douglas Crandall and Ed Thompson and Guido Bibra and Nancy Graziano and Andrew Planet and Amir Liv Baron. Cool, that's new. Peter Waldman, Tom Van Scotter, Tom Nathy, Oleg Straganov. Wow. Hey, everybody. Welcome to Astronomy Cast. Yeah, so tell me when you're ready and we will proceed with the
I
coordination.
think I'm ready. I'm checking my mic. Hold on. Well, yes, I actually am ready.
I'm recording.
The now I'm recording. Sort of. Go. Go. It's going. Okay.
Is it
Hi,
mono?
Preston. Yeah, I'm in mono.
Okay, good. I just want to make sure. Just gotta make sure. Astronomy Cast, episode 373, the Becquerel experiment. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Doing good, although it is that season. It's a season where we both complain about our allergies. So I'm going to complain about my allergies. I have allergies.
My eyes aren't watering today, but I have all the windows shut and I've taken all the allergy meds, all
Oh,
of them.
good. Good. Yeah, no, it's just in my. You can probably hear it in my voice a bit. There'll be a little bit of that. Cool. So let's just do, because this is what we do, let's do one more reminder about the upcoming Hangout-a-thon.
Yes, we have at the end of April the CosmoQuest Hangout-a-thon. It is April 25, 26. You can learn all about it by going to cosmoquest.org/hangoutathon, all one word. And we're still working on rounding up guests and door prizes, but it should prove to be an awesome 36 hours of me singing for our supper. It's kind of our hope that this is the last time we have to do this. I'm in the process of writing a ginormous NASA grant that if we get it, will mean we're back out of this hole that sequestration put us in 3 years ago. So help us survive just until we get this grant, hopefully, and if we don't get this grant, well, there's going to be a whole lot of rethinking how we do things.
More year after year, more hangout-a-thons then. Maybe we'll just do them for entertainment as opposed to raise money.
Oh, that would be awesome. That would be truly awesome.
Yeah. Okay, cool. So Antoine Henri Becquerel discovered radioactivity completely by accident when he exposed a chunk of uranium to a photographic plate. This opened up a whole new field of research to uncover the source of this mysterious energy. So this is a that's funny moment, which, as we've mentioned in the past, are probably our favorite kinds of discoveries. So when he performed this experiment, what was going on?
Well, it first of all wasn't so much an experiment as an odd accident. This was back in the 1890s, and everything was new. They were still working on figuring out photographic plates, photographic film, radiation, electrons, all of these things, particles. And we still didn't know all the particles that there were to find, and we still didn't know all of the things that particles could do, and atoms, and there was just so much going on. And Becquerel had recently seen a talk on X-rays. This was right after Roentgen had figured out that you could shine high-energy electromagnetic radiation, a fancy word for high-energy light, through someone's hand onto special film and could actually see the bones inside the hand.
With no ill consequences.
Well, yeah, this led to the crazy decades of things like using X-rays to make sure your shoes fit correctly and things that I don't think we'd quite be doing today. But yeah, so Becquerel saw this presentation on X-rays, and it got him to wondering about some effects he'd seen with uranium salt. And he had this notion that maybe the effects he saw from uranium salt were due to some sort of a phosphorescence process. Fluorescence, phosphorescence, these are processes where a material absorbs light and, in the case of fluorescence, emits it in real time at a different wavelength. So you expose a rock, a shirt, something to ultraviolet light, and then it gives off light, it re-emits the energy at a lower wavelength that in some really awesome cases is visible to the eye. This is where if you stand under a black light in the right white cotton shirt, you'll see your shirt as fluorescing in some sort of a purpley hue. Now with phosphorescence, it's a delayed response. So this is where you get calendars that glow in the dark. For instance, I had a Walt Disney one when I grew up, and it used to creep me out as a small child. In this case, the glow-in-the-dark paint, the phosphorescent paint, absorbs the daylight, the room light that hits it, and then when all of the lights are off, the molecules re-emit that light at a much slower pace, allowing you to see the glow-in-the-dark paint. So Becquerel was thinking, I wonder if one of these reactions, particularly phosphorescence, might be occurring with uranium salt. And he tried it. He exposed uranium salt to daylight, put it on film, and he got a kind of ghostly image. So he figured, well, maybe try this on an amazingly sunny day. He was working in Paris. He was working at the National Academy of Natural Sciences. And the particular day, he had his uranium salts and his films prepared, set up with a cross in between the salts and the film that he could use to try and image it as it blocked the high-energy particles. As he set up all of this, the sun kind of failed to come out. And so here he was with his film in the drawer, his cross in the drawer, his uranium salts wrapped up in black paper on top of all of this in the drawer, and no daylight.
Right. So we'll come back to this experiment later, right? He's like, we'll give this, wait till the sun is out again, and then we'll try it again later.
See, you'd think that. That would have made sense. That's probably what I would have done. But that's not what Becquerel did, and this is why we discovered radiation. Now, what actually happened is Becquerel had all of this and then decided to develop the film anyways.
To develop the film anyway, right? That's it. That's the moment. It's crazy to me that he did, because who would do that?
And it's effort. It's stinky, smelly effort.
Yeah. And there's not going to be anything on the film. It's why bother?
This is one of the many moments in science where I look at what folks were doing in the late 1800s and the turn of the 1900s, and I'm just sort of like, why? Well, thank you.
Right. I don't understand why, but thank you for doing that.
And so for whatever reason, back in 1896, he opted to develop film. And when he developed his film, he found a ghost of a smudge where the cross had been between his uranium salts and the film, and a darker smudge where it had simply been the uranium salt. And we actually still have that plate today. This is where we start to actually get photographic evidence of science, to be able to go and look at these things. And that's actually cool because you can look at the developed film and see his handwriting on it where he made notes. And this was that, this is weird moment that sometimes occurs in science.
Yeah, which heralds the beginning of the greatest discoveries. Okay, great. So he does this experiment in that he, for some weird reason, developed what should have been a completely blank piece of film, photographic plate. So then what? Now he's got this weird ghostly image, and so he knows. So I guess what's the conclusion that he reached?
Well, so what he presented on March 1st, 1896 was that there was the spontaneous emission of particles. His graduate student, who just happened to be Marie Curie, she named this radioactivity. There was spontaneous emission of particles that the film was able to capture. And then the true fun of sorting out what the insert expletives, probably in French, is going on moments began.
So please continue with these moments.
Well, so the first thing was to try and figure out, what is this? And they quickly realized that in this case it wasn't exactly X-rays like Roentgen had been working with, but this was something else. And as they started working with the uranium salts, they of course had to get more uranium. So this is where Marie Curie and her husband Pierre Curie actually went and did some mining, you might say. They went and collected uranium ore, processed it, and had the weird moment of, oh, it's not just the uranium that's causing this to happen. They actually found that in the garbage minerals they set aside, there was more radioactivity than in the uranium. And
did they realize that, I don't know, that the uranium had caused other things to become radioactive? Had they realized that it was, it's almost like that fluorescence, right? That it's the minerals store up the sunlight. In this case, they store up the radioactivity and release their own particles, right?
And they couldn't figure out everything that was going on, because one of the problems they kept running into is this was such a small fraction of the ore that it actually took years and years and years to pull apart all the minerals and figure out, okay, so the uranium is causing this. There's this stuff we didn't even know existed that we're going to call polonium. It's causing this other thing to happen. They started discovering radium, polonium, all of these radioactive elements within the ore, and starting to put together a story. Now, of course, they had to start to figure out what are all the different characteristics of these materials.
You hearing the sound in my background?
No, I didn't. What was that?
Oh, sorry. Sorry, Preston. Someone is building a concrete wall in my backyard, and or my backyard neighbor, and they're using some kind of grinder on these chunks of concrete. It's making a horrible noise. It's over now.
Okay, so back to, so I had just said they had to sort out what all of these strange materials were.
Yeah, yeah. Right. So I guess, each of the different radioactive elements on the periodic table of elements, right? It's gonna be radioactive in a different way, and so I guess their process now is to try and figure out how can they perceive the particles, the effect, what this radioactivity looks like.
And just as you're struggling to find words, they were struggling to find questions. And in the next round of, wow, that's cool that they sorted that, the next thing that they started to do was to try and understand, okay, what are the measurable characteristics of this radioactivity? And so one of their starting points was to take a radioactive element, whether it be the polonium, the uranium salts, whatever, and put it into a machine that allowed them to direct the particles through a collimator and then expose them to a magnetic field and then encourage them via the whole, once something's in motion, it goes in a straight line unless acted upon a force. Encouraged the particles via the magnetic force or lack thereof to hit a photographic plate. And what they found is some of the radioactive sources gave off particles that bent one way in relationship to the magnetic field. Some of them bent the exact opposite way. This indicated that some of the particles had a positive electric charge, some of them had a negative electric charge. And then some of them, they just went straight on through. They were completely unaffected by the magnetic field, indicating that they were charged neutral.
They had a neutral charge. That sounds similar to some kind of particle that we're aware of.
Well, in this case, it was actually just light, not neutrons. So this is where we ended up with the whole original concept of the alpha, beta, and gamma particles.
You're looking for me to, let's get started then.
So with
alpha.
So I have to start by admitting I utterly, totally, and completely screwed up my discussion of alpha, beta, and gamma particles a few episodes back. So if I am contradicting myself, it was because I had a moment a few episodes ago.
Old Pamela was, historic Pamela was wrong.
Historic Pamela was wrong. So
new Pamela's here to clear this up.
I am. So the alpha particles that they found, these turned out to be nothing more than ejected helium that came out of these large atoms as the large atoms broke apart into something new, something more stable, hopefully. Out popped a fast-moving, easy-to-stop helium. This got called alpha, and this is the particle that when I was young I was annoyed to learn was nothing more than, well, helium.
But just to be clear about this, right? This is this process of radioactivity where one kind of element decays into another kind of element, and the way it's doing this is by ejecting violently. Sure, parts of itself, right? And in some cases it's doing it proton by proton or neutron by neutron. In other cases it's doing it in big clumps. In this case the clumps are helium, which is what, two protons, two neutrons.
And this is where we get a positively charged particle that is radioactive.
Right. Okay. So we've got some alpha particles coming off. What else have we got?
So the other thing that we have is beta particles, and in this case, it's nothing more than an electron. This is where we get the negatively charged, high-speed particle coming out that can zot your DNA and cause cancer, as unfortunately Marie Curie discovered. But again, it's just an electron that's getting ejected at a high velocity from some sort of a radioactive decay process.
Okay, that's two.
And finally, what we have is gamma rays. This is where the decay process includes the emission of energy, high energy photons that very little is going to stop. It takes significant lead or concrete to prevent gamma rays from zotting your DNAs. With beta particles, all you need is heavy clothing. With alpha particles, paper or clothing will do it. Gamma rays, they'll just kill you.
Right, or turn you into the Hulk, right? Obviously.
Something.
Right. Okay. Right, and so, but the point being that the three particles are connected together, right? Like when you have the reaction, those three things will come out as part of this decay process, right?
And which ones you get depend on what the decay process is.
Right, exactly. So if you could sort of stick your detector in front of a hail of particles coming off some element, you would know what that element was based on what it was decaying into and the rates, things like that.
And the easiest way to tell them apart is you just look at, is this positively charged, negatively charged, not charged, and that tells you what you're dealing with. And the amount of these that you receive depends on how much of that radioactive ore you have and what its half-life is. And this is all stuff they were trying to figure out. The whole idea of half-life was something that came out of their research. And this all went fast and furious. And what really kind of amazed me was Becquerel and Curie, they won the Nobel Prize in 1903, just a few years after their initial announcement in 1896 of what they had discovered.
Okay, so hold on a second here. Let me just see if I got this straight, though. A researcher and his graduate student won the Nobel Prize together. Is that what you're saying? His female grad student.
I know. Isn't this exciting?
I know. That's the first and last time that has ever happened. No, I'm sure it's happened other times.
It hasn't happened often enough.
Right, but it definitely breaks the narrative that we've been going on to, which is that the researcher takes the credit many times. The grad student is the one who really comes up with the clever experiment. But I mean, Curie wouldn't have done it without Becquerel. I mean, without Becquerel kind of going, you know what, I'm going to do something really weird and develop a clean photographic plate. Wouldn't have occurred to her to start doing the research.
And what's amazing about all of this is this was really early on in the existence of the Nobel Prize. You see this example of an advisor and the grad students winning the prize for amazing research, fast turnaround, everyone being acknowledged. And it's just so sad that this precedent for awesomeness went away. Now, admittedly, Marie Curie, while getting the Nobel Prize for her research, also got cancer. So apparently, no story has a happy ending.
Yeah. But I guess it didn't even occur to them.
They didn't know.
Yeah, like before we do any experiments with this brand new amazing substance, let's pile a whole bunch of it next to some lab animals and see if there's any problem. And so but it's also kind of amazing to think that they got the Nobel Prize in the early 20th century for the discovery of it, and yet 40 years later it was used as the most powerful bomb ever created in war.
And it's true, the work that they did identifying radioactivity, the properties of energy being released as these atoms break into smaller pieces versus fission processes of smaller atoms combining and giving off energy as they form larger atoms. As these decay processes were discovered, they were putting together a whole new picture of how matter works. I don't think until their work came along that we really had this understanding that atoms weren't forever. they were the ones who started putting together that picture of things can transform one atom into another through these radioactive processes that conserve charge by giving off positrons and electrons, that conserve so many other properties that lead to child particles that we can start counting to figure out, well, carbon dating is possible due to looking at the child atoms that come from that decaying parent carbon.
And you also get situations like the discovery of neutrinos, which were fairly difficult to discover, but the math said they had to be there.
We needed that one more conservation particle. And all of this came out of essentially a photographic plate in a drawer with uranium salts and a cross.
Yeah. So, I mean, I'd love to sort of go a little deeper just into some of the other experiments that they went into. So once Becquerel had done that original discovery, once the Curies started to radiate themselves, what kinds of too soon? What kinds of experiments did that lead on to? What other parts of this did they uncover, and what did it lead to?
I think that starts to get to be an entire new show. I mean,
we've done one on radioactivity and
right. I mean, it went on to trigger Rutherford to start to do work where he was bombarding gold foil with alpha particles, and this allowed us to map out the shape of an atom. We couldn't have done that without alpha particles. We're going to be talking about more of these experiments as we go. It's kind of amazing to think that this also was what led us to start finding new atoms. We're now used to atoms get found by colliding things together in high energy accelerators. Prior to this, atoms got found by just kind of noticing the world around you was made of gold and silver and
right.
stuff. But Marie Curie went on to get a second Nobel Prize in 1911 because as they went through that ore looking for the uranium, they kept finding this other radioactive stuff and discovered this was new atoms that hadn't been previously classified. So this was simply foundational work that led people to literally go digging through rocks looking for things that fell apart in the night and gave off high energy particles.
Right. Which, of course, as we now know, are the remnants of supernova explosions, right?
And yeah, that's entirely true. Out of the Big Bang, we got hydrogen, helium, bits of lithium and beryllium. But everything else in the universe came from stars in one way or another. And all of these heavy atoms, all of these radioactive atoms, they came straight out of supernovae. And we actually use several of these radioactive atoms to start getting at the ages of stars in some cases, where we can start looking at the ratios of different specific isotopes of things like strontium to pull apart how old some stars are.
Well, I think that it's true, but I think it's a bit of a misnomer, because when you think about a main sequence star like our own sun, which is forming hydrogen into helium, when it runs out of that, it's going to start forming helium into heavier elements. But when it dies, it's going to hang on to it all. So none of that oxygen or carbon or any of that stuff that's in the sun is ever getting back out again, because it's just going to hold on with gravity.
It's trickier than that, actually. So there are two myths. One is all atoms come from supernova, other than the ones that came out of the Big Bang. And the other myth is that all the carbon stuff in a star gets re-released. It's actually somewhere in between, because in the outer atmosphere of stars, which are quite happily going to get emitted out in planetary nebula form, there are different reactions that go on. There's occasionally things like convective overshoot that can change the composition of the outer layers of the stars. All sorts of different things occur that do influence the composition of the atmospheres of stars, which do get given off to get recycled into planets and other stars.
So some of it is going to make its way back out into the universe.
Yeah.
Cool. Okay, well, I think after that complete diversion, I think we can wrap this episode of Astronomy Cast up. Thanks, Pamela.
Thank you. Did you have to keep muting your audio to deal with your neighbor's chainsaw?
No, I'll let Preston hack it out of the audio. It's very frustrating.
I'm sorry.
It's fine. It's going to be a ridiculous fence when it's done. It's going to be huge.
Are they at least putting like a large and interesting dog on the other side of it, or are they simply fence builders?
They do have it. Well, he works for a fence building company, and so
okay.
He's going to use his own product on his on the backyard. All right. Oh, I forgot to export.
Yesterday, I got to watch our friendly backyard groundhog happily climb our fence, use it as a lookout post to observe the neighbor's fledgling vegetables, and climb over the fence to go eat those fledgling vegetable plants that it had spotted.
That's
Fences
awesome.
Are no deterrent to happy little groundhogs.
Yeah, we don't have those here.
Oh, they're awesome. Ours is named George.
But hasn't he completely torn up your yard?
No. Oh. He happily lives back behind the garage and eats the weeds in the lawn and will eat vegetables if we don't basically ensconce them in chicken wire. But we're pretty good with the chicken wire.
Right, okay.
Our neighbors don't use chicken wire, so that makes it easy.
So he
just
can get
up and over the fence. Yeah.
He's a climber. Okay. Yeah, no, the thing that we have here that you have to worry about are deer. So if you have deer here, if you try and have a garden, the deer will get into it.
We have deer as well. And skunks and raccoons and moles and voles.
We don't have skunks.
Very
we do have raccoons.
Sparrow.
We don't have voles. Yeah. We have cougars, though, and bears.
We have those.
So
we also have coyotes.
Yeah?
We don't have bears.
Yeah, we also have wolves, but you never see them.
Yeah,
we have the highest, I don't know if I mentioned this in the past, we have the highest concentration of cougars in the world here on Vancouver Island. Yeah, and you never see them, but they always see you. So, cool. Okay, so let's take some questions. Ed Thompson notes that it's Happy Global Astronomy Month.
Yes, and in fact, our Hangout-a-thon is going to be joint with the folks from Global Astronomy Month, and we will be bringing in star parties from around the world as part of the Worldwide Star Party, or Global Star Party.
Guido Bieber notes, how can anyone be grumpy at you, Pamela and Fraser? 373 episodes. People, do that yourself, and then you can come and complain for taking 1 or 2 weeks off.
People just like to send us sad and hateful things. That's all.
Yeah, I know, and you especially. Totally. Okay, this comes from David Kuzinski. Totally unrelated to today's topic. Is dark matter in our galaxy distributed proportionally to baryonic matter? I.e., is there supposed to be more dark matter where there's more gas and dust, or is that relationship not that simple?
Yeah, we don't know yet. Still working on it.
But you can definitely see regions of more dark matter than others. We actually had on the Weekly Space Hangout about 2 weeks ago.
Within the galaxy or externally? Because I think within...
Well, so I guess, in our galaxy, we don't know. We can't really detect any of the dark matter inside the galaxy, but there is a dark matter galaxy orbiting the Milky Way. So
I would still be cautious of using the word dark matter galaxy. I'm much more comfortable with there is a blob of dark matter, because we also observe in the spaces between galaxies large clouds of hydrogen that haven't formed stars and gas, and we don't call those hydrogen galaxies. We call them clouds.
What looks like a place where all of the gas stars or the gas and dust was stripped away by the Milky Way, leaving the dark matter.
Yeah.
is what appears to have happened. So there's plenty of evidence that dark matter and its galaxies can be separated. So, and the bullet cluster is a great example of that.
Yes.
Right?
Yes.
So Tom Nathan notes, I would imagine that film at that time would have been very expensive, which is a really great point, right?
Yes. It was, but Becquerel was working at one of the leading institutions, so he was able to get his hands on things like film. He also came from a long line of physicists, so there was a certain amount of favor granted on seeing him be successful.
Ed Thompson asks, in honor of Global Astronomy Month, what is your favorite object to view through a telescope? What makes it so interesting to you? Okay, hold on. I wonder if we can guess each other's favorite object to view through the telescope. You probably know mine.
It's the Omega Nebula, isn't it?
No, it was two. One is Saturn.
Oh, yeah, I knew that.
And the other one is the Rosette. But you don't view it through a telescope.
I renamed it Omega in my head. I mixed the names of those two.
Yeah. You
Rosette. Even view both of them in that stupid, awesome video that Google did for us.
I know.
I'm a loser. Can you name mine?
Can I name yours? You like... No, I can't.
You should. I've mentioned it several times.
I'm going to guess Hyades?
It's really boring through a telescope. No, the Tarantula Nebula, because it looks like a tarantula through an actual telescope.
Yeah. That's cool. I've never seen it, obviously, because I've never left this hemisphere. What's yours, everybody? Okay, Amir Livnebaron asks, I'm sorry, I totally ruined that. Another question about dark matter. How do we know how far a dark matter halo of a galaxy extends? It can't be from the rotation speed of stars, since a spherical shell around the galaxy should exert zero total gravitational force on them. So how far does the dark matter halo seem to extend around a galaxy?
We're still figuring that out. We can see it more for galaxy clusters where we're able to use gravitational lensing. With things like our own galaxy, we have to rely on distant clouds that we observe in radio to start mapping out these velocities.
So many questions. Okay. Oleg Straganov says, is Earth's uranium made by neutrons or neutrinos?
I don't understand that question.
Yeah, it's made by supernova.
Right. Okay. And in some cases, uranium is produced from plutonium in nuclear reactors. Some of the breeder reactors do that, but that's a different question.
Yeah, so and
neutrinos don't build it. Neutrons sometimes do.
Right, but we did this. We've got a whole episode on supernovae, and we've got an episode on nucleosynthesis, and even another episode just about how some of the heavier elements are created.
Yeah.
But the gist is that, and tell me if I'm wrong here, right? When you've got a great big star and gets to iron in the middle, from the fusion, then the outward pressure shuts off, and the thing kind of the core falls in on itself, and you get some heavier elements there, and then it goes kaboom, and you get this pressure wave that moves back out through the star, and you get some more heavier elements there, and then
you actually also get a neutron flood, and it's this flood of neutrons that often very rapidly build up the cores of atoms, and through beta and inverse beta decay processes, you build up heavier and heavier elements.
And that's sort of what the Large Hadron Collider does, or particle accelerators, where they're throwing neutrons at things. They're trying to invent these exotic forms of matter by just throwing neutrons, and then just whenever they see that they got a lot of neutrons together, that's a new element. So. Well,
the neutrons have to decay into protons to get the new element, but yes.
But they had them there, but you won't know that you had them there until the decay happens, and you can see the decay particles, a la what we were talking about earlier, right? So in other words, you'll know the signature of the decay to tell you what element you had made.
Well, and sometimes you don't even have to wait for that. You simply build things up, build things up, build things up, and it's not from the decay into the child products. It's from you have a perfectly rational atom that you have now added far too many neutrons to. The neutrons then decay, giving off a electron and a proton, and the protons allow that old atom to become something new that, if we're lucky, is stable for a while. And we're actually hoping that as we climb up the periodic table, we're going to find another region of stability.
I was just about to ask you that question. Yeah, do you think that there is another place where there will be more stability, that these things won't decay?
In the place of wild hope, I leave room for both very heavy, stable atoms and planets out at 55 AU. Theory allows for both. I don't know if the theories are right, but I am hopeful of their discovery.
Do they know where they might, not the planets, the elements, do they know where they might show up on the periodic table? At what point you might reach stability?
You know, ever since high school, I keep hearing that, well, it's going to be found shortly. It's going to be the next thing we hit.
Yeah.
And since they keep changing where that island of stability is located, I simply sit here hoping that they find it. And other than that, going, theorists, please make up your minds.
Well, so I all hail Wikipedia. It's called the Island of Stability.
Yeah.
And they think it'll be in the 120 range.
But that think has moved a few times.
Yeah, so 118, man, these names are terrible. Okay, so like 100, fermium has a half-life of 100 days. 110, Darmstadium has a half-life of 3.7 minutes. While octium at 118 has 890 microseconds. So the half-life is just going down and down and down. Literally every single, not exactly, but most of them, you have a shorter half-life with each new element that you get to.
And the problem that we're running into is the gluons that hold the atom together have a very short distance over which they're able to exert their gluing the nucleus together force. And these atoms have nucleus that exceed the ability of gluons to reach across and hold everything together.
But maybe there'll be some nice configuration down the road. Peter Waldman likes M13, Hercules star cluster. Can't argue with that.
Yeah, that's a pretty one.
Ben Etherington likes the Orion Nebula because it was a guaranteed showstopper when the football players visited the observatory. Again, can't argue. Tom Nathy likes the Hickson 44 galaxy group. Andrew Planet likes the Earth. But you don't need much of a telescope to see the Earth.
You're expressing very Earth-centric ideas. Now, if you were on the moon, you'd have a different perspective.
I guess so. Let's see. Man, even the questions that people have been emailing in are kind of wrapped up. Cool. So is this a suggestion from Darren that we should do an episode on the hottest and coldest places in the universe and the solar system? And we actually did a video on that. Yeah. And the thing that I like about that is that the answer is probably for both is Earth. That the hottest place in the universe is probably Earth, and the coldest place in the universe is probably the Earth, unless there are aliens that are capable of producing hotter and colder things. Tell me I'm wrong.
I'm not sure on the hottest. I'm pretty sure that the hottest would be in the centers of galaxy clusters.
No way. No way. The Large Hadron Collider has generated temperatures that are, I think, in the trillions of degrees. It's crazy.
Oh, so you're not looking for sustained temperature.
No, no, just the hottest.
We actually, in one of the episodes of the universe that I did, we talked about the coldest places. But again, we were looking at sustained temperatures.
Yeah. And then, of course, the theoretical hottest temperature is what's it called? The Planck temperature, which is like 100 million, 10 to the power of 32 Kelvin. So that's, yeah, here we go. So the Large Hadron Collider hit 7.2 trillion degrees Fahrenheit, which I don't know what that is in Celsius. About the same.
Yeah.
So, hot, very hot. And then cold, obviously, you can hit just a fraction of a degree above absolute zero with lasers and Bose-Einstein condensates.
You get pretty close to that in a few places in the universe where you have cooling flows, but yeah.
Okay, so Amir's in Palestine, which is awesome. It's great to have someone from Palestine watching this live.
The internet is almost everywhere.
Almost.
I want to see an audience person from North Korea. That will make my lifetime.
Yeah, and Antarctica.
Well,
and
no,
the moon.
People watch from Antarctica. They just don't always respond. I'm not worried about Antarctica. It would be so cool, though, if we could start to reach behind these walls of stuff. Politics.
So, speaking of politics, let's end with a really controversial question here. So, what do you guys think is a good strategy? Get people and politicians back into funding space science, or wasting everyone's time and money on things like religious freedom laws?
Oh, God. Yeah, it's absolutely ridiculous. There should be no place for bigotry of any form in commercialism. The two don't match well. So let's just get.
I'm only going to sell pizzas to Pastafarians. That's it. If you're not a Pastafarian, then you can't buy my pizza.
Yeah, let's get all bigotry based on religion, race, gender choice, all of those different factors that are personal factors out of politics and capitalism. And
yeah,
you can pick who your friends are, you can't pick who your customers are. And yeah, let's do science.
Right? Yes. I mean, you could have just said, what do you guys think is a good idea to get people and politicians back into funding space science instead of, and then I just hazed on the rest of it. Doesn't matter. Yes, let's get some more space science.
Yeah.
Cool. Let me see. This is it. This is your chance, people. This is me running out of questions. So don't make me. Let's see what else. I've got anything over on.
I don't see anything on Twitter.
So Hal McKinney asks, are there a finite number of observed gamma ray frequencies?
No, it's a continuum. The problem is gamma rays just the energies just keep going. So we do hit a point where we don't have the technology anymore.
But is it in any way quantized, I guess, is the question. Do you know what I mean?
No.
Like it's a smooth.
So the gamma rays given off by a specific atom as it undergoes decay processes have quantized energies that correspond to the energy levels of the decay process. But gamma rays in general, because they can arise from a variety of different collisional processes and things that don't have these quantized energy levels. This means that gamma rays in general, as simply high energy forms of light, have a continuum spectrum, whereas you get a specific fingerprint of allowed energy levels out of different reactions.
Okay, here's the last question, and you brought this on yourself. Fred Miller wants to know, what is a cooling flow?
Easy way to think about it. If you take a can of compressed air, you spray the can of compressed air, the air that comes out of it is cool, and that's a cooling flow. It's because it's expanding, and as it expands, it gets gas laws cause the energy to get distributed, and the particles cool off as their energy gets distributed over a larger volume.
And so it has the potential to cool things that it passes through.
Mm-hmm.
Very cool. Very cool. Okay, well, let's wrap things up. So thanks, Pamela. Thanks, everyone, for watching. Weekly Space Hangout.
Friday.
Coming up on Friday, we've got a very special guest. I think it's Amy, who has transitioned from regular attendee to special guest. I don't know how she was able to make that transition.
Amy Titel?
Yeah. But the really cool one is going to be coming up. Let me just get my calendar here, because there's a really great. So Amy Shearer Title from Vintage Space, now working with Discovery, sort of our favorite space historian. Stephen Grenade is coming next week. Grenade.
Oh, he's awesome.
So that's awesome. Yeah. So he'll be on Friday, Stephen Grenade. We've got Amy Shearer Title the week after that, and then you're gonna love this. Baz Lansdorp from Mars One is gonna be our guest. It's going to be so much fun. We will interview him and talk about Mars One. So that's going to be in 2 weeks. Oh yeah, I'm super excited. So thank you so much, Pamela. Thanks everyone for watching, and we will see you all next week.
Thank you.